Okay, how you guys doing? All good things come to the end sometime. The last lecture. Some of you I see the first time, I think. Anyway, so today we'll talk about spin. Okay, and let me first give you a historical introduction. So how was spin discovered? The idea is very simple. So they did an experiment, Stern and Gerlach. In 1921. So what they did, they shoot silver atoms, right, that have configuration like krypton 4d10 5s1. So this is the most important part, because that's the electron outer sphere that was unpaired, and it has a angular momentum equal to 0 because it's an s electron, right? And so they shoot these silver atoms through the magnetic field, which presumably was like in z direction, right? So it's the north pole, this is south pole, and what happened? This flow of electrons, this array of electrons, it split into beams, right? And they localized somewhere here on the screen, which was sensitive to arrival of electrons. So that picture puzzled them, because simply that time people already understand that the Hamiltonian of the system should be a Hamiltonian of the atom, H0 plus magnetic field multiplied by angular momentum, right? So both are vector operators, and there was a so-called Bohr magneton. That's just a constant. Now if you have two vectors, B, which is bx, by, bz, and L that has also Lx, Ly, Lz, then the magnetic field they used essentially was 0, 0, bz, which I'll just call B, constant magnetic field, in z direction. Y, x, and y were 0. So therefore, from this to, we know the dot product, inner product of B vector with L vector will be what? How you guys doing? We're talking about spin. Okay. So
square root of bx squared plus lx squared by squared plus ly squared bz squared plus lz squared?
no, not really. So for those who joined, we have two vectors, B and L, both vectors in three-dimensional space. One is magnetic field. It has component 0, 0, B. B is some constant. And the second vector is L, which has component Lx, Ly, and Lz. We're considering inner product or dot product of those two vectors. What will be the result? BLZ, that is correct. How did you figure that out? Right, and whatever is multiplied by 0 is 0, right? So that's why Lx, Ly, they're multiplied by Bx and By, and that's why they're gone. So we have only BLZ part left, right? So Lz is still an operator. Now, if that operator Lz acts on s orbital, which is 5s in this case, right? So what will be the result? Lz acting on s orbital of function. What angular momentum does the s function has? Yeah, 0, right? So the result will be 0. So this term then, this term, when it acts on the 5s wave function, then it will produce 0. Essentially, the result will be the same as the original Hamiltonian of atom acting on 5s, and so this term should not really matter. In other words, magnetic field should not do anything to silver atoms because they have one electron, like unpaired electron, which is on s orbital, right? Now, why d orbitals will not matter? Our simple answer is d orbitals. You all know the picture with d orbitals, 5 d orbitals, say, and there is a Lz 0, Lz plus 1, Lz minus 1, and then Lz plus 2 here, right? And then minus 2. So since the d orbitals are all filled, so then there will be compensation, and so there will be no effect of the d orbital or any p orbitals which are fully filled. Whatever is in the krypton kind of configuration we have, there are p and d orbitals, so they all filled, and that's why they do not contribute anything here. That's why we are focusing on the one that is not completely filled, s orbital, and that's the only orbital that can matter potentially because it's not completely filled, but it doesn't matter according to this logic with magnetic field interacting with the angular momentum. And so the flow of electrons or flow of silver atoms in this experiment should not be affected by magnetic field. And the fact that the field actually split, the silver atom flow or ray, that actually puzzled people. That was a big deal. Okay, so they couldn't figure out what's going on. And then there was suggested a theory by Goldsmith and Uhlenbeck in 1925. The hypothesis was that actually this interaction is correct. It's just you need to account for the fact that L actually is not the only angular momentum that electrons have. There is also a spin operator that should be added to this expression. So this should be modified by this expression. Here we have L, S. The 2 is not essential right now. What is essential is we have on top of the angular momentum of electron, we have a spin internal angular momentum of electron. And that spin part, it should be half integer. In other words, when Bz interacts with the spin, we get the term like this: B times Bz times Sz. And when we have silver atoms with so-called spin up, then I will produce 1/2 Bz spin up, and when we have spin down, then we have minus 1/2 Bz spin down. So this up and down, in other words, they also called alpha and beta states that are eigenstates of Sz internal angular momentum of spin, right? So, and they are defined the way that Sz, when it acts on alpha, it produces plus 1/2, and when it acts on beta, it produces minus 1/2 Bz, right? So that's the idea of the spin. Now, how do we understand spin? Because what does it actually mean? This spin is generally a quantum concept, and it's difficult to understand, and difficult to connect with anything that we know in classical physics, for a simple reason that when it comes to angular momentum in general, right? So the easiest example would be if we consider Lz. What do we know about Lz? We solved the particle in the ring, and we found that the eigenfunctions in the polar coordinate system, I am phi, m can be any integer number, right? So then when Lz acts on them, what do we get? We get m phi, right? And so why it's difficult to understand what spin is because for the spin operators, they are acting on spin variables, okay? While angular momentum operates at least on some physical three-dimensional coordinates. In this case, for a particle in the ring, we have a two-dimensional problem, or at least the z-axis is third dimension, but we're working in the xy plane initially, then we go to the radial polar coordinates, right? And then we're analyzing what's the behavior of the function with respect to phi angle, right? Now, at least we can visualize what the functions are, how do they look, and what Lz does to them. Now, when it comes to spin, what is the variable that we call spin variable? Frequently it says, well, we have m variable, it can be 1/2, it's a discrete variable. That's one thing. So spin variable is a discrete variable, it only can have two values. Now the spin functions alpha and beta, they are not functions like this. They are defined that alpha 1/2 is 1 and alpha minus 1/2 is 0. Alright, so beta is defined as 1/2 is 0 and beta minus 1/2 is 1. Okay, so there are two functions, alpha and beta, and they are defined on this discrete variable. Now this discrete variable has a mysterious nature, it's just variable. Okay, so here I can show you, okay, this variable phi that I'm talking about, it's like angle on the 2D circuit, right? So you can see what the angle is. What this variable is, no one knows. Okay, so it's a discrete variable. Now this variable is not related to any of the components of 3D space. Okay, so it's the fourth dimension. Now when we talked about how to build the Hamiltonian of the system, of any system, I said, okay, well, every electron has r coordinate, and r is x, y, z, right? Well, what I said was not correct entirely, because indeed every electron has a coordinate r, say first electron, right, has x1, y1, z1, but also it has this m coordinate, which is a spin coordinate. So technically, the dimensionality of the wave function, if you have electrons in it, it should incorporate also the spin coordinate. So number of electrons in the molecule should be multiplied by 4, and that will be the dimensionality of the wave function that we're getting out of the electrons. Now with the nuclei, the situation is a little bit different, because nuclei, they also can have spin. Some of nuclei have spins, some of them don't. So it depends on the type of the nucleus. For example, hydrogen proton has a spin 1/2 as well, while the deuterium doesn't have spin. Okay, that's because elementary particles that are building those nuclei, they either have spin and they compensate each other, or they don't. So the nuclei can go either with factor 3, or if there are some magnetic nuclei, then you need to also incorporate spin, so that will be 4 per nuclei. But could be some non-magnetic nuclei with the factor 3, some non-magnetic, say, and there could be magnetic nuclei with the factor 4. So all that should be summed up in order to see what's the dimensionality of the total wave function. Okay? All right, so now that's the difficulty with the spin. Now I want to kind of demystify it a little bit, or tell you a little bit more about the angular momentum and how can we understand what spin is, essentially. It's a different perspective. Now, the difficulty of understanding quantum mechanics is that, say in classical mechanics, if someone asks you, does something move or not, how do you answer to that question? Based on what quantities? Compare the position, right? So you see the object at a certain time here, and later time you don't see it here, you see it somewhere else. Also you can, that's kind of a coordinate, right? Then also you can look at what? What else? Velocity, momentum, right? Kinetic energy. There are multiple quantities, right? Now in quantum mechanics, there is a somewhat separate ways of looking at the same question, whether object is moving or not. The most basic way would be to say, okay, well, the object is here at this time, and later time it's not here. So whether you have probability density, which is a function of time, or not, right? And we know that the answer is yes, and the answer could be no. Right? The answer is yes for what kind of functions? When your probability density depends on time. Eigenfunctions? Well, for the eigenfunctions, those are stationary states, right? So they have a spatial part, and then there's the exponent. And that exponent is not contributing if you consider probability density, right? So for stationary states, these are exactly these states, the answer is no. You don't have any time dependence if you look at the probability density. When do we have time dependence? Superposition on non-stationary states, right? Superpositions states on non-stationary. Then you have at least 2 components, and that's a general rule. Right? Different problems can have different eigenvalues of the time-independent problem, different eigenfunctions of time-independent problem, but the time dynamics always can be written like this for any function of the physical system, right? And then if you do the absolute square, you will still have time dependence. We've done it many times. Okay, so you see here, if we look at just the probability density, the answer could be no or yes. Now, you also mentioned that there is a different way of looking, just not on where the object is in a certain time, but rather momentum, kinetic energy, right? Those are things. And kinetic energy, I guess, is one, or angular momentum if the object is moving on the circle, right? So T, and let's consider also LZ or LZ square, right? So these quantities, they can be averaged, right? And if the average is non-zero, according to classical mechanics, the object is moving, right? Because this is average kinetic energy. If you kind of measure the kinetic energy of the wave function or the system you are investigating, and it's not zero, then it means that something is moving. Why are you looking confused?
No, I'm just remembering the question.
Okay. Okay, good. So Lz squared can be non-zero, or Lz generally can be non-zero. So then according to classical intuition, objects are moving. So now, if we're dealing with stationary states, then there is a clear contradiction, right? Why is there a contradiction? Well, because according to this criterion, object is not moving. According to this criterion, object is moving.
Quantum mechanics isn't classical mechanics?
Well, yeah. In short, that's the case. All right. So we have these different ways of looking whether things are moving or not, and this is more okay. So we have these operators that characterize. In classical intuition, they characterize movement. They can be non-zero, but based on the probability density, we're in a stationary state. And for particle on a ring, the eigenfunctions like that, right? Then what we would think about kinetic energy or angular momentum is that if m is non-zero, then the kinetic energy will be non-zero, right? Yes, no? No idea? All three answers are acceptable? What should be m to have a kinetic energy in particle on a ring problem? What's the kinetic energy expression for particle on a ring? Something related to the second derivative of angle, right? So for m non-zero, then kinetic energy will be something non-zero. And for m equals 0, then you get m outside. When you differentiate the exponent, then you get the 0 kinetic energy, right? Huh? About what? Yeah, that essentially falls to this contradictory category, right? So that the average of kinetic energy for non-zero m will be a stationary still state, so nothing is moving, but kinetic energy is non-zero, right? And so one way to think about where does this kinetic energy come from, or how to characterize kinetic energy of the wave function without having actually time involved, because there's no time in understanding this kinetic energy relation, then it's actually just looking on the wave function. Wave function looks different whether m is 0 or non-zero, and that difference is essentially could be understood if we look at the transformational property of the function. Now, if you have a function, you can characterize, even in classical mechanics, you can characterize if the object is moving, then its position is changing with time. Now, you can either think of it as position is changing with time, or you can think that when you move the coordinate system in the opposite direction, let's say, this direction, then the object will be exactly in the same place as we. So we started somewhere here. It moved, right, in the coordinate system, which was old one, x, y. Its position changed, but in the new one, y prime, x prime, the position is actually in the same place, right? Now, the movement of the object can be understood as if we move either object or the coordinate system, doesn't really matter. Then if we find the object in the same place, if we move the coordinate system, then it also means that the object kind of moved. Now, this view through the coordinate system helps us in quantum mechanics to understand the movement, because movement becomes not in time, but rather a symmetric property. And in the case of Lz, if you look at the wave function, it turns out what can be analyzed is how the function, if we move the coordinate system, we will get, say, a function dependence on the new angle. How is this related to the function with the old angle, right? And the new angle can be presented as old angle plus some delta phi, okay? So the question now is how the old function is related to the new function when we rotate it to coordinate system. And it turns out that analyzing that question helps a lot to understand what the wave functions and what the nature of the angular momentum without going into actually moving anything. So also it allows us to understand what Lz operator, how it can be used. And also you understand the spin better if we do that. Now the idea is very simple. If we take a function, we rotated the coordinate system, and now we want to express the rotated function as an old function, which was function at the angle phi, right? So how do we express this using this? Well, we know there is a Taylor series expansion, right? And so the new function will be an old function plus derivative of the function at the point of phi, delta phi, plus second derivative right, so on and so forth. Now this can be all written using the Lz operator. Why? Because the first derivative is just delta phi multiplied by I, right? Lz operator acting on psi. That's this expression. Second derivative will be I delta phi Lz squared applied to psi. Third derivative, and so on and so forth. Essentially, we can express now the new function as Taylor series, where we use Lz in the increasing powers. Now, how do we turn this into the finite expression? Turns out it's actually quite easy. You realize that this is nothing but just the exponent of Lz. Okay? So this is a very important relation. Also, it tells us how we can use Lz operator. So the importance of this relation is, say you have a wave function psi, could be particle on the ring, could be something, could be superposition of particle on the ring functions, doesn't really matter. So you have this function. Now you turn the coordinate system, and in the new coordinate system, you have the same function written, right? Then how do you express the new function using the old one? That's the expression in the sense that Lz, the meaning of Lz, if you exponentiate it and multiply by the angle, finite angle, it will tell you exactly what's happening with the wave function if you rotate the coordinate system. Now you can go and rotate the coordinate system by 2 pi and return to the same, essentially, coordinate system, right? You'd expect nothing to happen to the wave function. And we can check that. All right, let's put, instead of psi, let's just put this exponent of I m phi function, right? And so we have psi phi plus 2 pi is equal to exponent of I 2 pi Lz acting on the exponent of I m phi. We already know when Lz acts on this, how do we kind of apply the exponent of the operator on the function? Oh, it's actually quite easy. You go back to the Taylor series expansion, where all you need to do is to apply operator itself to the function, or square the operator on the function, and so on and so forth. Every time you apply nth power of Lz on our I m phi, what do you get? This is a very easy question.
You get I m psi to the n.
Yeah, almost. Just m to the power n, right? Because Lz, when it acts once, it generates 1m. If you act twice, you generate 2m's, and so on and so forth. So m into the power n. So therefore, when you do the Taylor series expansion like that and put the psi, which is an eigenfunction, then all you get, you can substitute essentially all Lz's by m, right? And then you can turn it all back into the exponential form. So you get I 2 pi m instead of Lz. Essentially, operator turns into the number when it acts on the eigenfunction, right? I m phi. So now we have just two exponents, right? So what do we have? If we combine them, we have one exponent I m, and then here phi plus 2 pi. And we know that this is equal to I m phi. 2 pi in the exponent with I, you can just do the algebra substitute. If you're not comfortable with the exponentiating 2 pi, you can go and use the Taylor's, not Taylor, but Euler expression for exponent of I 2 pi equals 2 cosine 2 pi plus I sine 2 pi, right? And that is 1. So what did we achieve essentially? So the Lz is an operator that tells you what's going to happen with the wave function when we rotate by a finite angle. If we rotate by, say, 2 pi, nothing's going to happen to functions of particle on the ring. Now, if we rotate by pi, things will start to happen on, especially for the functions where m is not 0, right? So because what we can see here is that if we apply I delta phi Lz onto the function of I m phi, we will get exponent of I m phi plus delta phi, right? That's what we're going to get. And this is the original function times what we can think of as a phase factor, I m delta phi, right? And if delta phi says pi, then the function can change the sign if m is odd number, right? Well, simply because exponent of I pi, if say m is 1, odd function of the p type, the m equals 0 can be considered as a S-type function. Nothing happens. It's like if you look at the function in kind of 3D space, it's like a ring because it's all the same, independent on what for m equals 0. Now, if we have m equals 1, then it's more like a p-type function because in this area it's positive, in this area it's negative, so it has a node. Now, if you rotate by pi, simply plus and minus will change. And what you get is this prefactor that will be -1. Okay? Now, the punchline here is that if you have electron and if you have spin, it turns out that the operator that is telling us what's going to happen to the function when we rotate by a certain angle is not just I delta phi multiplied by Lz. It also has an extra component that is called as, well, like an extra angular momentum component, which is Sz, right? Which acts on the spin part of the function. So this is a spatial part, but then there should be some kind of spin function. It's either, say, alpha function of m or beta function of m. And depending on that function, you will get an extra contribution when you rotate the coordinate system. Okay? So if you, the weird part of this, in this whole story of spin is that if you have one electron and you rotate the system of coordinates by 2 pi, you would expect to get the same function. But because Sz will generate 1/2 in the exponent, 2 pi factor that we were working before with, we had I m 2 pi, right? That was the factor. Now m in the spinor component will be 1/2. And that means there is no 2 pi anymore. There is only I pi, which is -1. So when you rotate the coordinate system by 2 pi, you are not going to get the same object. You're going to get the object with multiplied by -1. Okay? And that's the kind of a symmetric property of the electronic wave function. Yeah.
But if you rotate it again, you get.
If you get again 4 pi, then you get the object back. Yeah, that's the property. Now, what I don't like about spin, and the way it's presented in all quantum mechanical textbooks, I didn't see any textbooks which would present it differently, is that it's still not clear what is this variable and what are these functions. They are just abstract functions of discrete variable. Now it turns out, and the mathematicians, they have kind of simpler way to introduce spin. They call it spinor. And you can do it at home, so you can actually see that you can create the spinor object without going to the magical variables, which no one knows what they are, but rather you can see the same type of behavior with just the normal vectors, well, almost normal. So for that, let's consider just a three-dimensional space, right, x, y, z, and I will build you object, I'll call it zeta. That object, when we, it will be a function of two vector components. For like originally, let's say I have a vector x, and it's like a normal vector, x1, x2, x3, its components. Okay, and this is E1. These are basis vectors, E3, right? And I will build you a function that will change its sign when we change the coordinate system by 2 pi. Okay, so which is quite interesting, because if you think about it, you change the coordinate system by 2 pi, well, all the geometric objects should come back to what they are, because, well, nothing actually like really changed. But it turns out you can build such function that will change its sign, and here's how you do it. You need a little bit of complex numbers here, because the vector that I'm interested in has an interesting property that x1 squared plus x2 squared plus x3 squared equals to 0. So any vector with a real x1, x2, x3, if you have a condition like that, that would be a 0 vector, because that's essentially length squared for the vector. Now you need a complex x1, x2, x3, or at least allow them to be complex, and then the zeta function will be a square root of x1 minus I x2 divided by 2. Okay? So this is my function, and if I go and do the transformation that will change the coordinate system by 2 pi, how do I do that? Well, if I want to just rotate vector around, say, for simplicity, I will rotate it around the like this z-axis essentially, right? By 2 pi. So vector comes to itself, and, well, x will become x. Nothing will change. But this simple function, which contains the square root, will change its sign. Why does it do it? Well, mathematically, square root has 2 branches, essentially, plus and minus. And this continuous evolution just allows us to go from one branch to another. That's kind of the math behind this simple trick. But here's the trick. So if we say, when we start rotation, our new coordinates, x, well, essentially this vector will start changing coordinates, right? And these coordinates will be, say, if we use the matrix notation, the transformation will be cosine phi minus sine phi, sine phi, cosine phi. That's the typical rotation for within kind of 2-dimensional space. These are new components of our vector, right? And if you can see, if you phi goes from, say, 0 to 2 pi, so what happens to cosine? Cosine turns into 1, 1, 0, 0. So essentially x1 and x2 will come back to x1 and x2, right? But that's the rotation. But now let's see what's going to happen to our x1 minus I x2. That's the argument of the square root here. Okay. It turns out if we look at x1 minus I x2, the prime quantities, the one that you can build using this transformation, they will be equal to exponent of minus I phi unprimed quantities. For that, you can just use the, again, Euler expression. That's why we have exponent here, cosine and sine. They will build up that exponent because we have an extra I here. So that if you just do the algebra, then you can see that this is true. If you take a square root of this, right? So this will be kind of psi prime equal to square root of exponent is minus I phi divided by 2, and this will be the old psi. Okay, so this is the transformation property for the function that I'm building. And lo and behold, if you have phi that goes to 2 pi, it will be just reaching, this argument will be reaching only pi, not 2 pi, because of the square root, essentially. Yeah.
But the size, there's a half component there that's not.
Yeah, well, half component actually is not important because, yeah, you can divide by half. Half is not going to matter, really. Yeah, you can What is important is how x1 and x2 transform. They have this exponent of phi in front. So if you have half stays with this and forms like psi. So you can still write this. And the main point here is if you have psi that you arrive to when you rotate by 2 pi, it will be minus psi that you had originally. So this is essentially the simplest mathematical object, this function, for the vector of this type, which is called spinor. A spinor is called this object, right? Actually, turns out you can do plus or minus, then it will all work. But this is the math. The math is essentially that we have a square root there somewhere, and when we rotate the coordinate system, that square root allows us to change the sign. And interestingly, the object changes the sign when we go around. Okay, so something like that happens in the actual electron. It's just really hard to say what is it. It's almost like an electron has an extra degree of freedom. It's almost like electron has something inside, right? Another way to think about spin is like ball. Classical analogy would be a ball. If you throw a ball with a slight spin, rotation, right? So that would be angular momentum of the ball. But if inside of the big ball there is a small ball and also rotating in a certain direction, then the total angular momentum of that object will be sum of angular momenta, right? So it's almost electron has angular momentum which we see in the like in a coordinate space, x, y, z, physical space, and also there is an extra angular momentum that is internal. That's why it's called spin. But nothing actually moves. It's more the symmetric property. Okay, so you can see this not by thinking that electronic wave function is actually spinning, but rather you can think of it as there is electronic function, and if you rotate the system of coordinates, then you will have new representation that will be old one multiplied by some phase. Okay, and that phase is usually given by the angular momentum, total angular momentum multiplied by angle. Okay, so that's the idea. What else? What else do you want to know in the last 5 minutes? I can tell you about Schrödinger's cat, which to me is actually quite simple if you think about it. So everyone is making a big deal out of Schrödinger's cat and will tell you that oh, this is like something that is hard to understand. But in reality, it's a relatively simple thing, because I think the mistake of Schrödinger, like you probably know the story, the Schrödinger came up with this idea that okay, there is a cat, and if you put the cat in the box and also add there the radioactive atom, and the radioactive atom can decay, and when it decays, it's kind of it kills the cat through some device, essentially, that detects that the radioactive atom decayed, and so it's time to kill the cat, right? But it's all in the box, you don't see it. So you have a cat, radioactive atom, and the device that kills the cat when the atom kind of decays. So the atom is the quantum system, and so we don't know whether it's decayed or not. It can be in a kind of superposition. And that makes essentially a cat, because cat is connected with the atom, in a superposition of life and dead cat. Okay, so that's the how do we really think about dead and alive cat at the same time? So it seems like a very strange thing. But in reality, if you think about it, we all are in a superposition of dead and alive, because dead and alive are not eigenstates. Like really, like the state of alive, like you, me, everyone, we are in a superposition state because we're evolving. if we were in the true eigenstates of the Hamiltonian of the universe or whatever, right, or whatever Hamiltonian, then we would be static. Nothing would happen in our lives. Like, we would not have thoughts, we would not move, like, we would be stationary states, right? So the state of life or state of death doesn't really matter, because when you die, you still decay, right? So worms eat you and so on and so forth, right? So things move on, even if you die. So dead or alive state, it's not really an eigenstate, it's a superposition state. So we are evolving, all our life is evolution of the superposition state. Now, what we have in this problem from the quantum mechanical perspective, the cat is evolving, atom is evolving, because this decaying atom, if you think quantum mechanically, there is a barrier for the decay of the atom. Atom is like a quantum system that tunnels through the barrier, and then it's considered to be decayed. But this potential, if you kind of solve it, like we solve the particle in the box, but you can also solve the potential, which looks like this. And the eigenstates will be delocalized actually through the whole thing. And only you can build the localized wave packet that lives for some time by making a superposition of states. Okay, so the atom that hasn't yet decayed, it's also a superposition of states in the problem that will eventually evolve, tunnel through the barrier, and we call this superposition decayed, this superposition not yet decayed, right? So then the whole problem of Schrödinger's cat is kind of a two-dimensional problem, where one dimension is a dimension of the atom decay, and another dimension is a cat life and death kind of path, right? And so the cat is going from life to death. Well, there is eventual death for the cat. It doesn't really matter whether you put it with atom or not, right? It's just the second coordinate of atom, can accelerate that dynamics, right? So that's what is happening. Essentially, quantum dynamics of superposition states, atom and the cat, and just one dynamics can accelerate another. It's the same as like if someone puts the gun to your head and press the button, then, well, they just accelerate your transition from life to death situation, right? So there's nothing really happening, nothing surprising really happening. They just kill you, and then your evolution is just much faster from death to alive, from alive to death state, right? So it's very simple. So the same thing here. No big paradox, no big trouble. It's just people kind of start thinking about, oh, what does it mean, life and the dead cat superposition, start fantasizing and became confused. And but if you think about this in terms of eigenstates and in terms of what is happening in quantum mechanics, there is no really a big deal. It's just the evolution of two quantum systems, both in the superposition states. Okay? Any questions, comments? Because the time is up. Yeah.
Yeah, office hours next week.
Okay, so as I put on a blackboard, there will be a tutorial, right? Next Monday. So yeah, I'll probably be around, but just direct your questions to TA. That's the preferable course of actions. Okay. And I guess I'll see you guys on exam, which will be next week, right? Next Thursday, yes. So the exam is posted. Now, one thing to remember is that a previous exam, probably definitely 2015, was a 3-hour exam. So that's why it's longer. So it's not going to be that long no, this year. So it will be a 2-hour exam. So, but I don't remember 2016, was it 2-hour or 3-hour? So, but I'll try to make it well, appropriate for 2 hours. Okay. All right. See you.